In fluid mechanics, the Reynolds number is a dimensionless quantity that is used to help predict similar flow patterns in different fluid flow situations. The concept was introduced by George Gabriel Stokes in 1851, but the Reynolds number is named after Osborne Reynolds, who popularized its use in 1883. The Reynolds number is defined as the ratio of inertial forces to viscous forces and consequently quantifies the relative importance of these two types of forces for given flow conditions. Reynolds numbers frequently arise when performing scaling of fluid dynamics problems, and as such can be used to determine dynamic similitude between two different cases of fluid flow. They are also used to characterize different flow regimes within a similar fluid, such as laminar or turbulent flow. Laminar flow occurs at low Reynolds numbers, where viscous forces are dominant, and is characterized by smooth, constant fluid motion. Turbulent flow occurs at high Reynolds numbers and is dominated by inertial forces, which tend to produce chaotic eddies, vortices and other flow instabilities. In practice, matching the Reynolds number is not on its own sufficient to guarantee similitude. Fluid flow is generally chaotic, and very small changes to shape and surface roughness can result in very different flows. Nevertheless, Reynolds numbers are a very important guide and are widely used. Definition: the Reynolds number can be defined for several different situations where a fluid is in relative motion to a surface. These definitions generally include the fluid properties of density and viscosity, plus a velocity and a characteristic length or characteristic dimension. This dimension is a matter of convention. For example, radius and diameter are equally valid to describe spheres or circles, but one is chosen by convention. For aircraft or ships, the length or width can be used. For flow in a pipe or a sphere moving in a fluid, the internal diameter is generally used today. Other shapes such as rectangular pipes or non-spherical objects have an equivalent diameter defined. For fluids of variable density such as compressible gases or fluids of variable viscosity such as non-Newtonian fluids, special rules apply. The velocity may also be a matter of convention in some circumstances, notably stirred vessels. The Reynolds number is defined below for each case. Flow in pipe: for flow in a pipe or tube, the Reynolds number is generally defined as where is the hydraulic diameter of the pipe, its characteristic traveled length, is the volumetric flow rate, is the pipe cross-sectional area, is the mean velocity of the fluid, is the dynamic viscosity of the fluid, is the kinematic viscosity, is the density of the fluid. For shapes such as squares, rectangular or annular ducts where the height and width are comparable, the characteristical dimension for internal flow situations is taken to be the hydraulic diameter, defined as where A is the cross-sectional area and P is the wetted perimeter. The wetted perimeter for a channel is the total perimeter of all channel walls that are in contact with the flow. This means the length of the channel exposed to air is not included in the wetted perimeter. For a circular pipe, the hydraulic diameter is exactly equal to the inside pipe diameter. That is, for an annular duct, such as the outer channel in a tube and tube heat exchanger, the hydraulic diameter can be shown algebraically to reduce to where is the inside diameter of the outside pipe, and is the outside diameter of the inside pipe. For calculations involving flow in non-circular ducts, the hydraulic diameter can be substituted for the diameter of a circular duct, with reasonable accuracy. Flow in a wide duct: for a fluid moving between two plane parallel surfaces where the width is much greater than the space between the plates then the characteristic dimension is twice the distance between the plates. Flow in an open channel: for flow of liquid with a free surface, the hydraulic radius must be determined. This is the cross-sectional area of the channel divided by the wetted perimeter. For a semicircular channel, it is half the radius. For a rectangular channel, the hydraulic radius is the cross-sectional area divided by the wetted perimeter. Some texts then use a characteristic dimension that is 4 times the hydraulic radius, chosen because it gives the same value of ρ for the onset of turbulences in pipe flow, while others use the hydraulic radius as the characteristic length scale with consequently different values of ρ for transition and turbulent flow. Flow around airfoils. Reynolds numbers are used in airfoil design to manage scale effect, when computing comparing characteristics. Fluid dynamicists define the chord Reynolds number, R, like this: R equals Vc/I1/2, where V is the flight speed, C is the chord, and I1/2 is the kinematic viscosity of the fluid in which the airfoil operates, which is 1.460 x 10⁵ m2 per second for the atmosphere at sea level. In some special studies a characteristic length other than chord may be used. Rare is the span Reynolds number, which is not to be confused with span-wise stations on a wing where chord is still used. Object in a fluid. The Reynolds number for an object in a fluid, called the particle Reynolds number and often denoted rep, is important when considering the nature of the surrounding flow, whether or not vortex shedding will occur, and its fall velocity. In viscous fluids, where the viscosity is naturally high, such as polymer solutions and polymer melts, flow is normally laminar. The Reynolds number is very small and Stokes' law can be used to measure the viscosity of the fluid. Spheres are allowed to fall through the fluid and they reach the terminal velocity quickly, from which the viscosity can be determined. The laminar flow of polymer solutions is exploited by animals such as fish and dolphins, who exude viscous solutions from their skin to aid flow over their bodies while swimming. It has been used in yacht racing by owners who want to gain a speed advantage by pumping a polymer solution such as low molecular weight polyoxyethylene in water, over the wetted surface of the hull. It is, however, a problem for mixing of polymers, because turbulence is needed to distribute fine filler through the material. Inventions such as the cavity transfer mixer have been developed to produce multiple folds into a moving melt so as to improve mixing efficiency. The device can be fitted onto extruders to aid mixing. Sphere in a fluid. For a sphere in a fluid, the characteristic length scale is the diameter of the sphere and the characteristic velocity is that of the sphere relative to the fluid some distance away from the sphere, such that the motion of the sphere does not disturb that reference parcel of fluid. The density and viscosity are those belonging to the fluid. Note that purely laminar flow only exists up to ρ equals 10 under this definition. Under the condition of low ρ, the relationship between force and speed of motion is given by Stokes' law. Oblong object in a fluid. The equation for an oblong object is identical to that of a sphere, with the object being approximated as an ellipsoid and the axis of length being chosen as the characteristic length scale. Such considerations are important in natural streams, for example, where there are few perfectly spherical grains. For grains in which measurement of each axis is impractical, sieve diameters are used instead as the characteristic particle length scale. Both approximations alter the values of the critical Reynolds number. Fall velocity. The particle Reynolds number is important in determining the fall velocity of a particle. When the particle Reynolds number indicates laminar flow, Stokes' law can be used to calculate its fall velocity. When the particle Reynolds number indicates turbulent flow, a turbulent drag law must be constructed to model the appropriate settling velocity. Packed bed. For fluid flow through a bed of approximately spherical particles of diameter d in contact, if the voidage is I micron and the superficial velocity is versus, the Reynolds number can be defined as or. The choice of equation depends on the system involved. The first is successful in correlating the data for various types of packed and fluidized beds, the second Reynolds number suits for the liquid phase data, while the third was found successful in correlating the fluidized bed data, being first introduced for liquid fluidized bed system. Laminar conditions aptly up to ρ equals 10, fully turbulent from 2000. Stirred vessel. In a cylindrical vessel stirred by a central rotating paddle, turbine or propeller, the characteristic dimension is the diameter of the agitator. The velocity is whereas the rotational speed. Then the Reynolds number is. The system is fully turbulent for values of ρ above 10,000. Transition and turbulent flow. In boundary layer flow over a flat plate, experiments confirm that, after a certain length of flow, a laminar boundary layer will become unstable and turbulent. This instability occurs across different scales and with different fluids, usually when, where is the distance from the leading edge of the flat plate. and the flow velocity is the free stream velocity of the fluid outside the boundary layer. For flow in a pipe of diameter, experimental observations show that for fully developed flow, laminar flow occurs when and turbulent flow occurs when. In the interval between 2300 and 4000, laminar and turbulent flows are possible and are called transition flows, depending on other factors, such as pipe roughness and flow uniformity. This result is generalized to non-circular channels using the hydraulic diameter, allowing a transition Reynolds number to be calculated for other shapes of channel. These transition Reynolds numbers are also called critical Reynolds numbers, and were studied by Osborne Reynolds around 1895. The critical Reynolds number is different for every geometry. Pipe friction. Pressure drops seen for fully developed flow of fluids through pipes can be predicted using the Moody diagram, which plots the Darcy-Weierspach friction factor against Reynolds number and relative roughness. The diagram clearly showed the laminar, transition, and turbulent flow regimes as Reynolds number increases. The nature of pipe flow is strongly dependent on whether the flow is laminar or turbulent. Similarity of flows. In order for two flows to be similar, they must have the same geometry, and have equal Reynolds numbers and Euler numbers. When comparing fluid behavior at corresponding points in a model and a full-scale flow, the following holds. Quantities marked with M concern the flow around the model and the others the actual flow. This allows engineers to perform experiments with reduced models in water channels or wind tunnels, and correlate the data to the actual flows, saving on costs during experimentation and on lab time. Note that true dynamic similitude may require matching other dimensionless numbers as well, such as the Mach number used in compressible flows, or the Froude number that governs open-channel flows. Some flows involve more dimensionless parameters than can be practically satisfied with the available apparatus and fluids, so one is forced to decide which parameters are most important. For experimental flow modeling to be useful, it requires a fair amount of experience and judgment of the engineer. Smallest scales of turbulent motion. In a turbulent flow, there is a range of scales of the time-varying fluid motion. The size of the largest scales of fluid motion are set by the overall geometry of the flow. For instance, in an industrial smokestack, the largest scales of fluid motion are as big as the diameter of the stack itself. The size of the smallest scales is set by the Reynolds number. As the Reynolds number increases, smaller and smaller scales of the flow are visible. In a smokestack, the smoke may appear to have many very small velocity perturbations or eddies, in addition to large bulky eddies. In this sense, the Reynolds number is an indicator of the range of scales in the flow. The higher the Reynolds number, the greater the range of scales. The largest eddies will always be the same size. The smallest eddies are determined by the Reynolds number. What is the explanation for this phenomenon? A large Reynolds number indicates that viscous forces are not important at large scales of the flow. With a strong predominance of inertial forces over viscous forces, the largest scales of fluid motion are undamped or there is not enough viscosity to dissipate their motions. The kinetic energy must cascade from these large scales to progressively smaller scales until a level is reached for which the scale is small enough for viscosity to become important. It is at these small scales where the dissipation of energy by viscous action finally takes place. The Reynolds number indicates at what scale this viscous dissipation occurs. In physiology, Poisson-Ewell's law on blood circulation in the body is dependent on laminar flow. In turbulent flow, the flow rate is proportional to the square root of the pressure gradient, as opposed to its direct proportionality to pressure gradient in laminar flow. Using the definition of the Reynolds number, we can see that a large diameter with rapid flow, where the density of the blood is high, tends towards turbulence. Rapid changes in vessel diameter may lead to turbulent flow, for instance when a narrower vessel widens to a larger one. Furthermore, a bulge of atheroma may be the cause of turbulent flow, where audible turbulence may be detected with a stethoscope. Derivation. The Reynolds number can be obtained when one uses the non-dimensional form of the incompressible Navier-Stokes equations for a Newtonian fluid expressed in the Lagrangian derivative. Each term in the above equation has the units of a body force with the same dimensions of a density times an acceleration. Each term is thus dependent on the exact measurements of a flow. When one renders the equation non-dimensional, that is when we multiply it by a factor with inverse units of the base equation, we obtain a form which does not depend directly on the physical sizes. One possible way to obtain a non-dimensional equation is to multiply the whole equation by the following factor, where is the mean velocity, or, relative to the fluid, is the characteristic length, is the fluid density. If we now set, we can rewrite the Navier-Stokes equation without dimensions, where the term, finally, dropping the primes for ease of reading. This is why mathematically all Newtonian, incompressible flows with the same Reynolds number are comparable. Notice also, in the above equation, as the viscous terms vanish. Thus, high Reynolds number flows are approximately inviscid in the free stream. See also, Reynolds transport theorem, drag coefficient, deposition, notes. References. Further reading, Zagarola, M.V. and Smits, A.J., Experiments in High Reynolds Number Turbulent Pipe Flow. AIAA Paper No. 96-0654, 34th AIAA Aerospace Sciences Meeting, Reno, Nevada, January 15, Euro 18, 1996. Jeremy M., Fluid Mechanics, a course reader, Mechanical Engineering Department, University of Canterbury, 2005, ppd 5.10. Hughes, Roger, Civil Engineering Hydraulics, Civil and Environmental Department, University of Melbourne, 1997, ppA 107 Euro 152, Foos, Infos Fluid Mechanics, Mechanical Engineering Department, University of Oxford, 2001, PA 96, E. M. Purcell. Life at Low Reynolds Number, American Journal of Physics Vol 45, ppA 3 Euro 11, 1, Trusky, G. A., Yuan, F., Katz, D. F. Transport Phenomena in Biological Systems, Prentice Hall, ppA 7. ISBN 0-13-042204-5. ISBN 978-0-13-042204-0. External links, the Reynolds number at 60 symbols.